Page 11. Okie doke. So, what we've been doing so far this unit is we've been finding area under a curve, either by using geometry and adding up areas to find the exact area, or estimating that using rectangles or trapezoids. And again, just like the warm-up problem we just saw, if we're given a velocity graph, this would tell us something like displacement. If this were some sort of gallons per hour, this would tell us how many gallons were lost or gained or whatever. So we are now going to be able to do this for not any function. Actually, it's not possible to take the integral of every function, but a whole bunch. We're going to add a whole bunch. And we're going to start by learning how to do indefinite integrals. So what an indefinite integral is a function that represents the antiderivative of a given function. Which we can use to find the area under the curve. This is the same idea, but in reverse of what we did with derivatives. So a derivative represents slope of a tangent line, right? So if we have f of x equals x squared, f prime of x is 2x. This is a function that represents the slope of the tangent line at any point, right? If we took this function right here, and we have our graph y equals 2x, and we integrate this, we would get x squared. I'll put an asterisk by that. X, let's say we get x squared. We will, but it could be x squared plus 1, x squared plus 2, x squared plus 3. It could be a lot of different versions of x squared, but let's say it's x squared. X squared would be a function that could tell us the area under 2x between any 2 points that we could find. So it could tell us that area, which that's taking the definite integral. X squared would be the indefinite integral. It's the function that just allows us to do that. Okay, so the reason I put an asterisk by that is because, well, I'll just put it here. Our integral is not actually x squared, it's x squared plus c, where c represents some constant that we don't know. And I can put that on here too. So, for example, in number 1, what function has a derivative of 7? 7x. Now, we're going to write 7x plus c, but think about this for a second. What's the derivative of 7x plus 1? What's the derivative of 7x plus 10?
7.
What's the derivative of 7x plus 101?
7.
Or 1011?
7.
Still 7, right? So that constant could be anything. We don't know what it is. So there's basically an infinite number of functions that have a derivative of 7. So we're going to put plus c. And we don't know what c is, and it is possible to find c depending on certain information, but it's not possible in any of these. So this is why it's called an indefinite integral. It could be a lot of different functions. Sometimes this is called the general solution to a differential equation. We'll talk more about that later. So, or it's called the general indefinite integral, or just the indefinite integral. So it can be called a few different things. Okay, so in general, there's lots of different ways to think about integrals, but one main way is like, okay, what did we take the derivative of to get this function, right? We're doing backwards derivatives. Sarah.
Like, is there anything you have to like label that the equals like this,
I'm putting this equal sign to go with that expression right there. Yeah. So think about this. If we have x to the fifth, turn to your neighbor. What did we take the derivative of to get x to the fifth? See if you can think about what that would have to be. Very good.
Look at this kid. What a smarty. That's why it helps out. Yeah. 6 plus c. Yeah, plus c, plus c, plus c, plus c.
Okay, so
I just wrote that like it's natural.
what's the derivative of x to the sixth? 6x to the fifth. Okay, so this is not 6x to the fifth, it's x to the fifth. What do we need to go with x to the sixth?
1/6.
Yeah, 1/6, or x to the 6 over 6. Yes. Okay. So it's basically like we're kind of accounting for the fact that we have to do the power rule. We're thinking about what that number must have been to be out front so that it would cancel out once we took the derivative. We need plus c. So please remember plus c. So do number 3. All right, did you guys get 1/13 x to the 13th plus c? Nice. Okay. What we're using is the reverse power rule. It's the power rule reversed. Here's our process for when the powers get a little more difficult. It's like fraction powers, negative powers, etc. So that you're not keeping it all in your head. Here's your step-by-step process. It's increase the power by 1. Then divide by the new power. Again, for a lot of these, you're going to be able to just do that in your head, and that's great. Like when I get to number 4, oh, it's 1/5 x to the 5th minus 1/3 x cubed plus c. But once we start getting into negative powers, fraction powers, powers that are pi, it's a little more helpful to think, okay, increase the power by 1, like plus 1 to the power, divide by whatever that new power is. Okay. So let's do the problems on this page, the rest of these problems. And all right, check your answers. Also check my work, and just in case I did these fast and maybe made a mistake. And if there's any of these we want to check, go over them. Obviously, for some of these, there's more than one way that you could write them.
Yeah, no, we have to make the ones where oh wait. It's just 3 over 24.
Should round
Yep.
for number 8 versus negative x squared over 6. I guess over 4.
Over 4. Yep. That's right. That's over 4. Let me know if you guys find anything else. Or if we have any questions or ones that we want to see me go over. Be careful, pi is just a constant. So like number 11 just becomes x root pi, adding x to the constant there. Is that okay? Can I hide the top 2 there? Yeah. For this one here, like when there's fractions involved with the constants too, this is when I'm like, okay, increase the power by 1, divide by the new power. I say that to myself just to keep up step by step.
That's what I was thinking. Yeah.
Okay with these? All right, let's look at the next page. With your group, without reading this yet, no spoilers. You can read it if you want. I want you guys to see, like, what do you think the integrals of these two would be? Like, what would you guess? It's on the next page. You can read the top sentence if you want, but see if you can get it. Okay, so I'll show you guys how to do these. If you're reading the sentence up there, it is going to tell you how to do them. But what do you guys think about my number 14 here? Talk about it with your group. Does that work? The bottom.
Oh, what is split?
Like, if it's splitting the denominator would be like if it's x over x plus 1, this does not equal x over x plus x over 1. That's what splitting the denominator means. Don't do that ever. I'll put a squared in there just so they look different. Okay, what do you guys think? Is that the integral of number 14? Is that going to work? Yeah, okay, so maybe there's some sort of quotient rule that we could do. So first of all, if what I did was I did the reverse power rule for each term, right? If I was going to check my answer, what would I do? Take the derivative. How would I take the derivative of that? Quotient rule. And so what should I get on the bottom of my fraction if I'm doing quotient rule? The bottom squared, right? Which would be x to the, well, just, I guess just quick, what is this squared? Yeah, this 1/25th x to the 10th. Okay, do we have that on the bottom right there? Do we have x to the 10th? Okay, no. So we can see, I mean, like, quotient rule would be crazy with this. Crazy with this, right? It would be really complicated fractions. The 10th power, hello, that's a lot. Okay, so no, this is not what we're supposed to do. Could we somehow, maybe, like, this is a quotient, so maybe we could, like, reverse engineer this and figure out what we must have used the quotient rule on to get to this. So, like, the bottom could be something like x squared, right? Because we have x to the 4th. We're undoing it. Then we have to sort of try and figure out what the top could be. So somewhere on there would be like the derivative of the top times x squared minus 2x times the top. And maybe we could mess around with that to get, to like reverse engineer the quotient rule here. It actually probably is possible with this, but I don't want to do it. That sounds hard. So what this illustrates is that some integrals, like, you can't just run it back and undo the derivative. Like, reverse power rule is great. When we have a single term that we're doing, we have something like, 4 over x cubed, we can undo the power rule and get right to that, because it's already kind of set up as though the power rule was just done. Basically, every other integral is really complicated because maybe there was some sort of complicated derivative that was taken and then it was simplified down to something that we can't just like undo. So we need some different strategies with integrals. Basically, the only rule that you guys have right now is reverse power rule. Next class, we're going to learn U substitution. So you'll get another rule that you can do, but that's actually just reverse power rule, but fancy, and the reverse chain rule. So we don't have any other rules other than reverse power rule. Reverse power rule is not going to work on any of these in the form that they're in right now because they're not single terms. Like, I can't just do 1/3 2x minus 3 cubed. I can't just reverse power rule that whole thing because if I take the derivative of that, I get 2x minus 3 squared times the derivative of the inside, which would be 2, and that doesn't match what we were given. Now maybe that's enough information to tell us, oh, it should just be 1/6. Yes, you're correct. What you just did was U substitution, but no spoilers, we'll do that later. So we have to use some different techniques. We have to get them into terms that look like this, ax to the n, just by itself. This is when reverse power rule works. And the reason I'm spending a lot of time on this is because there's definitely a tendency with integrals to just use whatever rule you feel like using because it's complicated. But let me just tell you, integrals are complicated. They are way harder than derivatives. Some are impossible. So the process is just going to be more complicated. So you just have to embrace that. And it's going to be more work to take integrals. So that's just the facts. So with this one, we're going to need to FOIL this for now. Next class we'll be able to do U substitution, but we have to multiply this out, and we have to do 4x squared minus 12x plus 9. I think. Did I FOIL that out right? Yes. Okay. So now we could use reverse power rule on each of those because they're separate terms. For number 14, what are we going to do? Okay.
Split it into different fractions.
Yes. We are going to split this into some different fractions here, and then we're going to simplify. Whoa. Now we can use reverse power rule because we have separate terms. They're all in this form. This is a really common technique. What are we going to do in 15? We're going to do both, right? It says it right there. So we would need to multiply the top out, then divide everything by x to the 1/2. So go ahead and do that with 15. Get it so that we can use the reverse power rule. Okay, here's what I got. So we FOIL the top, and we should get 5x squared minus 11x minus 10 on top. Is that what we got? Did I do it right? 6. Minus 6. Hello. What? 6x. Oh, a classic blunder. The old 2 times 3 is 5. Rip. Okay. 6x squared minus 11x minus 10. Right? Okay. Those are all being divided by x to the 1/2. Remember, when we divide, we subtract exponent powers. So if I split the fraction, or if I just distribute the divided by x to the 1/2 to each, I'm subtracting 1/2 from each of those exponents. So this becomes 6x to the 3/2 minus 11x to the 1/2 minus 10x to the negative 1/2, or 10 over root x, or 10 over x to the 1/2, however you want to write it. But now we can use the reverse power rule here, because each of them is a separate term in this form, a times x to the n. Now for each of these, we could increase the power by 1, divide by the new power. But we literally cannot take the integral of this until it's in this form. It's impossible. And we're going to run into that with integrals. With derivatives, derivatives are great. You personally will be able to take the derivative of, I don't know, 90% of functions by the time you're done with AB Calc. That's probably accurate. And every function can have the derivative taken of it. That is not true for integrals. It doesn't work cleanly in reverse. Some functions are just too complicated or too simple to take the integral of. So we have to use a bunch of different tips and tricks here. Questions on that? Okay. I want us to look at some of these next problems here. Right here, what we are given is an initial value or an initial condition. What this does is it allows us to solve for C. So I want you guys in your group to try number 16. See if you can solve for C. Or see if you can find f of x. That's what we're looking for. We're looking for the function f of x. Okay, when you guys did this, did you guys get c equals -1? Okay, so we take the integral, we plug 2 in for x, we set it equal to 3. We solve for c, we get c equals -1. Our final answer here is 3/2 x squared minus x minus 1. This is what's called the particular solution, often. Particular solution. So we have the general solution that has plus c. Particular solution is like a specific equation that fits that. We need some sort of initial value in order to find particular solutions. But that's what it would be. Okay. Yeah.
Is the definite integral the same as the particular solution?
No. The definite integral is the specific area under the curve.
And that's for a specific interval.
Yes, between two points, yeah. Two values, between two given values, yeah. Okay. I'm going to leave those other problems for you guys to do as like extra practice as you're studying for things.